Dear physics aspirants, right now I have the physics book of +2 level, and here you will see the figure of Carl Friedrich Gauss, born in 1777 and died 1855. He was a child prodigy and was gifted in mathematics, physics and engineering, astronomy, and even land surveying. The properties of numbers fascinated him. Use and his work he anticipated major mathematical development of later times along with Wilhelm Welcher. He built the first electric telegraph in 1833. His mathematical theory of curved surface laid the foundation for the later work of Riemann. Riemann. Today I am going to discuss magnetism and Gauss law. In chapter 1 we studied Gauss law for electrostatic. In figure 5.3c we see that for a closed surface, figure will provide you the information 5.3. 5.3 figure is here, you will see respectively, and you will see here the field lines of bar magnet, a current carrying finite solenoid, and electric dipole at large distances. The field lines are very similar. The curves labeled and are closed Gaussian surfaces. You will see here. The represented in the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no matte change is enclosed by the surface. However, in the same figure for the closest tube, there is a net outward flux, since it does include a net positive charge. The situation is readily different for magnetic fields, which are continuous and form closed loops. Examine the Gaussian surfaces represented 1 on 2 in figure 5.3, which we have seen in the previous pages, or the figure 5.3. Both cases visually demonstrate that the number of magnetic field lines leaving the surface is balanced by the number of lines entering it. The net magnetic flux is 0 for both the surfaces. This is true for any closed surface. You will see here the angle with theta. Figure 5.6 will provide you the information regarding what I am discussing. Consider a small vector area, scalar and vector, to be studied by you, because scalar and vector will provide you the information here. The consider a small vector area element as of the closed surface. As in figure 5.6, the magnetic flux through AS is defined as, you will see the magnetic flux symbol is equal to B point S, where B is the field at AS. We divide S into many small areas, elements, and calculate the individual flux through each. Then the net flux is, magnetic flux is, you will see summation. You will see here with the 5.9 equation will provide you the 0. Magnetic flux, you will see here is the 0. Summation mark is here. All given here, where all stands for all area elements. S dash you will see here, and compare this with the Gauss laws of electrostatic. The flux through a closed surface in that case is given here, summation E point as you will see Q by electromotive force, and where Q is the electric charge enclosed by the surface. The difference between the Gauss laws of magnetism and that for electrostatic is the reflection of the fact that isolated magnetic poles, also called monopoles, are not known to exist. There are no sources or sinks of B. The simplest magnetic element is a dipole of a current loop. All magnetic phenomena can explained in terms of the arrangement of the dipoles and the current loops. Thus Gauss law for magnetism is the net magnetic flux through any closed surface is zero. So the specific aim is here to understand the subject matter. The net magnetic flux through any closed surface is zero. You will see here. This example will provide you the information magnetic flux and is equal to zero, and the summation is total. Here you will see the example 5.6. Many of the diagrams given in 5.7 show is 5.7 show magnetic field lines, thick lines, and in the figure wrongly point out what is wrong with them. Some of them may describe electrostatic field lines correctly. Point out which ones. You will see here, and you can see and try to understand what is given here, and it will provide you the better understanding. Solution is here. Wrong magnetic field lines can never emanate from a point as shown in figure over any closed surface. You will see here. Over any closed surface, the net flux of B must always be zero. Pictorially, as many field lines should seem to enter the surface at the number of lines leaving it. The field lines shown in fact represent electric field of a long positively charged wire. The correct magnetic field lines are circling the straight conductor as described in chapter 4. Chapter 4 of magnetism and matter of physics plus 2 level. When you study, then Gaussian surfaces will be required and Carl Henrik Gauss will to be studied. So magnetism and matter is the subject of physics, and subtopics we have discussed Carl Friedrich Gauss as magnetism. Magnetism and Gauss law we have studied. Next level of discussion will be the Earth's magnetism. So magnetism and Earth, what is the relationship between these two? We will discuss, and we will get information regarding the magnetism and matter of physics topic, physics subject regarding the Earths. We will meet in the next discussion with lot more. Till then, thank you. Thanks for watching the video.